you can see these contours of likelihood of the value of these two quantities. So in this case, you can see indeed that the most likely value here in the peak of this contour is around 35 solar mass versus a secondary mass of a little bit under 30 solar mass. Okay, and you can do the same thing on the right. And here we have the so-called spin plots. So this is, roughly where we think the spin values are and in which plane, which angle. Okay, so this is so far what has been published. And so on the y-axis, you can see the mass of the object. And so you can see two objects then going into a third object. So these are the original two masses. And then at the top of the arrow, you can see their final mass. And so this is more or less the landscape of events that we've detected. And then in the other colors, you can see some of the more astrophysical, so non-gravitational wave detections. And so you can see that we've, to date, we have seen a lot. I think it's in the order of 50 events that we have seen so far. So this really is opening up the era where we can start to do some statistics with respect to these binaries and black holes in general. Okay, so what I'm going to do in the coming perhaps 10 minutes, I'm going to give you a quick overview of some of the notable results. And again, I want to stress that this is by no means exhaustive. Okay, but still, I wanted to mention some of it, some of the highlights that we've seen. So the first one is what we call 150914. For those who are interested, this is actually just a date stamp. So it's 2015, September 14. So this is, of course, the landmark first detection. And it has allowed us to do very exciting things like start putting constraints on a dynamical nature of space-time, right? Because with these signals, we are able to track the two black holes all the way up to the moment when they collide. And so in this space, the gravitational field and the gravitational, the velocities are very high. So we have 170608, and this is one of the first black holes that puts us in the range of what we've seen in the electromagnetic band, so like X-ray binaries and so on. And so this is a relatively low mass binary. The first 3 detector network, and then let me explain a little bit about this. So the LIGO detector actually consists of 2 detectors, one in Hanford, one in Livingston, and 170814 is the first time that also Virgo participated. So Virgo is an Italian detector that Virgo participated in the detection. So that's why we call it a 3 detector network observation. Okay, 170817 was actually a really exciting event. And this was actually the first time that we've observed a binary neutron star in gravitational waves. And so you can indeed see the masses here. So M1 on the x-axis, M2 on the y-axis. And you can see these probability distributions. And so depending on whether we put any constraints on the spin, so if we assume that it has to have low spin, we have the blue. If we assume that it can have almost maximal spin, then it's in red. And you can still see that in either cases, the masses are very comfortably within the order of a solar mass. And so this is an indication that we're dealing with a lower mass compact object, and we think this is a binary neutron star. In particular, because we've also observed an associated gamma ray burst and a kilonova. So what we see here on the right is the sky map, so the area in the sky where we think the signal originated. And so you can see the LIGO sky map in green and the LIGO Virgo sky map in darker green. And then you can see some of the electromagnetic observations that have been done to put, for example, the gamma ray burst in a particular plane of the sky. And so when all of these overlap, that gives us a bigger confidence. So here on the right, you can actually see some of the optical work that was done in pinpointing the actual location of this event. And indeed, in and around the time of the gravitational wave signal, there appeared a very bright little dot here. So you can see on the both sides where one you can more or less see it and the other one you don't. And so all of these observations came together. And so this event, this gravitational wave event, was associated with a gamma ray burst as well as a so-called kilonova. So this has allowed us to do quite interesting studies, including probing the nuclear equation of state. So suppose that these are actually neutron stars and they collide, then they actually give us information about so-called tidal deformability. So how easy it is to deform a neutron star, which then is related to the equation of state. And so here we actually see the constraints that we have put on the so-called tidal deformability parameter, lambda, and again for the first object in the x-axis and the second object in the y-axis. And you can see that, that the signal was not very informative, but nevertheless, we're able to at least put some upper limits on how compact or not compact the system is. Now, in light of also having observed this signal in the electromagnetic spectrum, that actually means that we have enough accuracy to do a so-called Hubble constant measurement. And this principle is related to the fact that in gravitational waves, you can fairly directly get a probe of the luminosity distance, right? And that's because we understand the intrinsic luminosity, and we can measure how much we observe on Earth. So that's how you get the luminosity distance. And then if we can pinpoint the galaxy, we can observe the redshift, and we can combine those two to get a Hubble constant measurement. Now, this was actually in blue. You can see the actual measurement that was done. You can see that it still is very broad, especially compared to some of the modern measurement by both Planck and using supernovae. But you can see that it still falls nicely within the observed values in these two experiments. Another thing that we've been able to do is constrain the speed of gravity. So this is actually looking at how long, what's the time difference between the arrival of the gravitational wave signal and the arrival time of the light. And this has to take into account some of the effects of where the light and where the gravitational waves are produced. Nevertheless, given the distance that we know that this signal originated from, we can set fairly tight constraints on the difference in speed between the photon and the graviton. Okay, so moving on, now it goes even further in time. We can actually see so-called 1904-12 and 1908-14. And these were the first ones that had significant asymmetric masses, meaning that the mass ratio of the system is actually relatively high. And what that means is actually that we can start to observe some of the subdominant effects of gravitational wave emission, so-called higher modes. So here you can indeed see that the Q, which is the mass ratio, is significantly different from 1. And using that, we've been able to, for example, observe or give some evidence that we've observed a subdominant mode, in this case, the 3-3 mode. So what we show here is that the rho on the x-axis is the so-called signal-to-noise ratio. So you can see that if you have the 3-3 mode is associated with quite a lot of signal-to-noise ratio, and definitely in the dashed line you can see the expected noise distribution. This is beyond what we typically expect that noise can induce. Okay, moving on, we have 1905-21, and this has actually been a very high. This is a very high mass event, and at least one of the masses we think falls within the pair instability mass gap. And so here on the x-axis, you can see some of the heavier systems that LIGO has observed, and you can see their masses, and you can indeed see that it was the heaviest mass, uh, and it would fall into this parent stability mass gap. Okay, 2001-05 and 2001-15, and this is actually what we think is the first time we've observed, or there's um, indication that we've observed a so-called neutron star binary. So if you look at the masses, then one of the masses is firmly within the neutron star mass range, whereas the other one is in the black hole mass range. And so we have not been able to directly observe some of the tidal disruption, but nevertheless, if we just look at the masses, this seems to be consistent with a so-called neutron star binary. Sorry, neutron star black hole binary. Okay, so I want to switch gears now, and I want to talk a little bit about the prospects, about what we can expect to see in the coming years. And this is a fairly biased view. I only have time to talk about two things. So I'm going to talk a little bit about what I find interesting. And so again, I don't want to make out that this is the most promising work, but it's definitely work that I found very interesting. So the first one I want to show is a search for ultralight bosons. And again, this can be done in many, many ways. This is a nice figure from Bertone, and you can see some of the some of the effects that some dark matter candidate will have on some of the observational in the observational regime. And so what I want to show you is that through the measuring the black hole spin, as I showed before, you can actually start to constrain some of the dark matter candidate. So the mechanism that I want to focus on is the so-called superradiant instability, and in particular, the critical spin that arises from it. And so the situation I want to highlight is that we have, for example, a black hole, and if there's if ultralight boson exists, then under the right conditions, you get this superradiant instability, so that you can actually form a cloud, an ultralight boson cloud around the black hole. But in forming the cloud, you extract some of the spin from the black hole. And so what you end up seeing is that the spin of the black hole, if there is this superradiant instability, and if the ultralight boson exists, then there's going to be a critical spin. So above that, we don't actually expect there to be black holes with that spin. So that's the mechanism that I am considering. And so what happens here, this is a little bit more schematic. So if you have on the x-axis the mass, and on the y-axis the spin. So if the initial black hole is, let's say, it falls here, right, upon formation, then when you have this instability, you create this cloud around the black hole, and the spin drops to a particular value until an equilibrium is found. And so the expectation is that depending on the mass, we have a particular upper limit on the spin. And with a whole set of measurements of black hole masses and spins, this actually is something that we can probe. And so what we expect to see is that indeed, if this is the spin distribution, let's say the a priori spin distribution, then we expect all the spin values, the possible spin values, to collapse upon this critical spin value, and so we expect to see an excess in black holes with this spin. So I don't want to go to all the details, but what I'm showing here is a simulated situation about on the x-axis is the number of signals that we observe with signal to noise ratio above, let's say, 30, and then here on the y-axis is the evidence for the existence or the non-existence of this ultralight boson. And you can kind of see that we need in the order of 100, 200 signals in order to start constraining some of the mass of this ultralight boson. So this is just to give you a sense of what can be done when we go to, let's say, 100, 200, or even 1,000 detections. Now, we've actually done the actual measurement using the the catalog, or the set of detections that we've had so far. And so here on the x-axis is the mass of the ultralight boson, and on the y-axis is the probability. So given the data, how likely is it that it has this particular mass? And so one thing I wanted to highlight is if you look at the blue distribution, which is the full catalog, you can actually see that there's a particular range that is particularly disfavored. And so this would actually be, you can see this as an exclusion, that we don't expect the ultralight boson to have this mass because it's not consistent with the population of masses in spin that we found. So that's here on the ultralight bosons. And again, this is just a snapshot. There's actually there's a lot more work and a lot more probes. Adrian, I think, has shown something in his talk yesterday, but there's many more ways in which we could hope to probe a hypothetical ultralight boson. So in the remainder of my time, I want to talk a little bit about something else, which also ties with some of the things that Nick said yesterday. But in this case, we're looking at lensing of gravitational waves. And so one of the things that we've done within the collaboration, we've also looked for signatures or potential signatures that there could be some intervening mass. So in this case, we look at a source here on the bottom, and on the left side, you can see the source. And then there could be some intervening mass, for example, a galaxy, and then the detector is here. And so we can see a gravitational lensing of gravitational waves. Now, there are many different effects here. You can see on the bottom, you can see some of the effects that have been observed in the electromagnetic spectrum. But maybe more importantly is that by finding lensing, we could do very interesting work. This includes fundamental testing some of the fundamental aspects of gravity, including, for example, the polarization content. We can use lensing to do a localization of merging black holes, because they don't actually, we don't expect them to have a electromagnetic counterpart. We can do precision cosmology, but we could also look at some of the micro lensing population as well. So again, in the interest of time, I won't go through everything, but we have considered, for example, the putting constraints on the lensing rate, right? So assuming or not assuming that lensing actually occurs, we can put here in the bottom right, we can put constraints on the rate of lensing that we have observed. We actually also search for multiple signals. So imagine again that we have we have one source over here, and then we have an observer here. And so with lensing, it could actually appear to be several images or several sources coming with a particular time delay and a magnification. So what we see in the detector would then be a signal here, and then with some time delay, another duplicate signal somewhere else, but perhaps with a different magnification. So one thing that we did, for example, is we looked at all the detections that we have, and we compare their intrinsic parameters, because we expect those to remain the same in lensing, and then ask, okay, how likely are all of the ones that we've detected, how likely are they going to be pairs of each other, right? They're counterparts of each other. And if you look at the very right column, that's more or less the base factor, the evidence for this, and you can see that they are all more or less negative, meaning that there is no significant evidence that these are auxiliary pairs. We can also use the actual detections and try to go deeper into the data to see if there's some signals that we wouldn't have detected without this lensing hypothesis, but that we will be able to lift above the noise if we know the thing that we're searching for. So here we're also showing some of the most promising candidates. of these so-called subthreshold triggers. Again, we did analyze them further, and none of them have any conclusive evidence that they are lens signals. But still, we have released these for people to follow up if they are interested. Okay. Finally, we've also looked at so-called microlensing effects, and so this is, if you will, sort of interference of gravitational waves. And so we have the detector here, and so rather than seeing distinct different images, we have all the summation of all the effects of different images into an interference pattern. So here on the bottom left, you can see the original gravitational waves, but now with this interference pattern. And what you see is actually a beating pattern that is superimposed on the signal. And so what we can do is we can look for, we can dig into the existing detections to see if there's any evidence for these beating patterns. And that's what's shown here. So on the x-axis, on both sides, you can see the estimation of the mass of the lens. And here we've assumed a so-called point mass lens. And then here on the right, you can see a number, which again is the evidence, the degree to which we think this microlensing is happening. And again, you can see that they are more or less around the 0 mark, meaning that there's no evidence for these so-called microlensing effects. Okay, I think pretty much my time is up, so I'll leave it at this, and I'd be happy to take any questions that you may have. Thank you.